Welcome to Nemo's World. It's me, Nimesh Naik. Today I am discussing CSIR Net Questions, December 2018. Topic Real Analysis. It's a part B question. Question: define f of x is equal to 1 by root x for x greater than 0. Then f is uniformly continuous. Option number 1 on this interval 0 infinity. And option number 2 on this interval close to r to infinity for any r greater than 0. And option number 3 on this interval open 0 and closed r for any r greater than 0, and option number 4 only on the intervals of the form closed interval a b for 0 less than a less than b less than infinity. So in this question we want to find in which of these following interval the given function f of x is equal to 1 by root x for x greater than 0 is uniformly continuous. So first of all we want to know what is uniform continuity of a given function. So definition: uniform continuity. Let f from x to y, where x and y are the subset of R, be a function. Then f is uniformly continuous if for all epsilon greater than 0 there exists a delta greater than 0 such that modulus of f of x minus f of y which is less than epsilon whenever modulus of x minus y which is less than delta for all x comma y belongs to x. So from this question we have given that f of x is equal to 1 by root x for x greater than 0. So considering the graph of f of x by drawing we get the graph of f of x be like this. So from the figure it is clear that f has a vertical asymptote. So from this we can directly conclude that which is not uniformly continuous on the interval 0 infinity. Otherwise we can considering a neighborhood of 0. So in a neighborhood of 0, by considering a neighborhood of 0 the function has a sudden increase, that is function is sharply increases when in a neighborhood of 0. So we can say that the function is not uniformly continuous on the interval 0 infinity. That is, the function is sharply increases on a neighborhood of 0. Therefore, it is not uniformly continuous on the interval close open 0 infinity. More clearly, we are considering f from open interval 0 infinity to r by f of x is equal to 1 by root x, because we are considering this function is uniformly continuous or not within the interval 0 infinity. So we are defining f from open interval 0 infinity to r. Now we are considering two sequence xn and yn in open interval 0 infinity such that sequence xn is equal to 1 by n square and sequence yn is equal to 1 by 4n square. Now we are computing modulus of xn minus yn, which is equal to modulus of 1 by n square minus 1 by 4n square, which is equal to modulus of 3 by 4n square, as n tending to infinity, which is will approaches to 0. Therefore we can say that modulus of xn minus yn, which is less than epsilon naught. Now we are taking epsilon is equal to epsilon naught is equal to 1 by 2, and modulus of f of xn minus f of yn, which is equal to modulus of 1 by n minus 1 by 2 by n. This is f of xn, which is equal to 1 by root of 1 by n square. So it will become 1 by n, and f of yn, which is equal to 1 by root of 1 by 4n square, which will become 1 by 2 by n. So which is equal to modulus of n minus 2n, which is equal to n, which is greater than epsilon naught is equal to 1 by 2, because as an n tending to infinity it will approaches to infinity. That is, there is an epsilon naught and two sequences xn and yn in open interval 0 to infinity such that limit n tending to infinity modulus of xn minus yn will approaches to 0, and modulus of f of xn minus f of yn, which is greater than epsilon, because we get modulus of f of xn minus f of yn, which is equal to n. As n tending to infinity it will be approaches to infinity. Therefore we can say that modulus of f of xn minus f of yn, which is greater than epsilon for all n belongs to n. Therefore f is not uniformly continuous on open interval 0 infinity. So our first option, which is says that the function f of x is equal to 1 by root x, x greater than 0 is uniformly continuous on open interval 0 to infinity, but here we get f is not uniformly continuous on open interval 0 infinity. Therefore our first option is also wrong. Now we are going to our third option, which is f is uniformly continuous on this interval open 0 and closed R for any R greater than 0. Okay, now we have this interval is a subset of open interval 0 infinity, and we have given that we have get f is not uniformly continuous on open interval 0 infinity, implies that f is not uniformly continuous on open 0 and closed R such that R greater than 0. Therefore our third option is also wrong, because which says that f is uniformly continuous on 0 to R for any R greater than 0, because by observing the graph of 1 by root x, we seen that while choosing a neighborhood of 0, the function have a sudden increase, that is sharply increases in a neighborhood of 0, therefore which is not uniformly continuous in that neighborhood. Therefore we can eliminate our third option. Now before going through the second and fourth option, we want a result which says that f from x to y is differentiable and modulus of f dash of x which is less than or equal to m, which implies that f is uniformly continuous. That is, f from x to y is differentiable and f dash of x is bounded, which implies that f is uniformly continuous. Now we are considering f from closed R to infinity, that is from this interval where R greater than 0 to R by f of x is equal to 1 by root x, and we are applying this result for checking f is uniformly continuous or not within the interval R to infinity where R greater than 0. So we are computing f dash of x. F dash of x is equal to minus 1 by 2 into x power 3 by 2. Now modulus of f dash of x is equal to modulus of minus 1 by 2 x power 3 by 2, which is equal to modulus of 1 by 2 into x power 3 by 2. Now we are considering this interval close to R to infinity where R greater than 0, and this is maximum when the denominator is least, so that is when x is equal to R. So that is modulus of f dash of x which is less than or equal to 1 by 2 into R power 3 by 2, because I choosing x is equal to R, so I get modulus of f of x which is less than or equal to 1 by 2 power 2 into R power 3 by 2. So I choose this term as a m, so taking this is equal to m, that is we get a mod f dash of x which is less than or equal to m, that is mod f dash is bounded. Then by using the above result we can say that f is uniformly continuous on closed R to infinity where R greater than 0, because we are considering R greater than 0, that is we get f is uniformly continuous on the interval close to R to infinity where R greater than 0. Now our second option, which says that on the interval close to R to infinity for any R greater than 0 f is uniformly continuous. So it is a true option, therefore our second option is correct. And our fourth option, which says that only on the interval of the form closed interval a to b, closed interval a b for 0 less than a less than b less than infinity, this is true, because f of x is equal to 1 by root x is uniformly continuous within this interval a to infinity for 0 less than a less than b, and this belongs to our second option. This interval belongs to our this interval, since it is a part b, it's a true statement, and which also belong to our second option, and it is a part b question, so we are taking more precise answer. So our more precise correct option is on close to R to infinity for any R greater than 0, f of x is equal to 1 by root x is uniformly continuous. So our second option is correct. So correct options of this question is option number 2. Okay, thank you. If you like my video, please subscribe my channel and also share with your friends and like.